The problem statement for this exercise is pretty easy. I just need V of t, which is the voltage across this capacitor, as a function of time for t greater than 0. First, let's look at the circuit and see what's going on. So let's take a look at the circuit for t greater than 0. At t greater than 0, this switch is in this position. The source is isolated. I have a 3 ohm resistor. The switch is connecting that to this 6 ohm resistor. I have a 2 farad capacitor and a 1 ohm resistor. Now the first thing we probably want to do is stare at this circuit for a while and see what's going on with it. I have one energy storage element, which means that this is a first order circuit. The energy storage element is a capacitor. That means that this circuit's going to have a time constant, which is the equivalent resistance of the capacitor times the capacitance. There's no source connected to the circuit. That means what I'm going to be looking at is a natural response. So the natural response of an RC circuit, the form of the solution, is going to be V of t is some initial voltage e to the minus t over tau. Now all I need are numbers for V0 and tau. I've already decided that tau is going to be the equivalent resistance seen by the capacitor times the capacitance. So let's calculate an equivalent resistance, which is going to be the Thevenin resistance seen by the capacitor. So pull the capacitor out. So if I do KCL here, these resistors share the same current. They're in series, so this becomes a 9 ohm equivalent resistance. Then that's going to be in parallel with this one, so REQ is going to be the product of the two. 1 ohm times 9 ohms over 1 ohm plus 9 ohms. So this is 9 over 10 ohms. So tau is going to be 9 over 10 ohms times 2 farads, which is 1.8 seconds. Now we need an initial condition. For our initial condition, we rely on the fact that the capacitor can't change its voltage instantly. So take a look at the circuit for t less than 0. In fact, what I want is the voltage across the capacitor at t equals 0 minus just before the switch moves. So I have a 5 volt source, 3 ohm resistor, a 6 ohm resistor. Now at t equals 0 minus, I'm going to assume this switch has been in position A for a long time and that everything has become a constant. So the capacitor looks like an open circuit, and here's a 1 ohm resistor. Everything in here is in series since there's no current through an open circuit, so this is a voltage divider, and V of t equals 0 minus is the voltage across this. So V at 0 minus is equal to 5 volts times 1 ohm over 1 ohm plus 6 ohms plus 3 ohms, or 10 ohms. So this is 0.5 volts, which is exactly V at 0 plus, since the capacitor can't change its voltage instantly, which is the initial condition V0. Now I have a number for V0 and I have a number for tau. So V of t is equal to 0.5 e to the minus t over 1.8 volts for t greater than 0. These problems are starting to become a little bit more complicated. They have multiple parts. We have to identify the form of the solution. We have to figure out how to find a value for tau. We have to find an equivalent resistance. We need an initial condition, and finally we need to plug everything into the equation correctly. So it's probably a good idea to start double checking things a lot. So let's take a look at an alternate approach towards this problem that we can do some cross-checking with. So let's write a differential equation for this circuit. So, as usual, the circuit for t greater than 0 has this switch in this position. There's no source connected. I have a 3 ohm resistor. I have a 6 ohm resistor. I have a capacitor that's 2 farads. And I have a 1 ohm resistor. I'm interested in the voltage across the capacitor, V of t. And if I'm going to write a differential equation, I'm going to need the voltage-current relationships for the capacitor. It's probably easier to draw those directly on my diagram. If this is V of t, the current through the capacitor is going to enter the positive voltage terminal, and it's going to be 2, which is my capacitance value, dV by dt. Now all I really need is KVL, KCL, and Ohm's law. Let's do KCL up here at node A. I can combine these into an equivalent 9 ohm resistor on this side of the capacitor. So the current through here is going to be V of t over 9 ohms, plus the current through the capacitor is 2 dV dt, plus this current here is going to be V of t over 1 ohm. That equals 0. Now, this is pretty good news because this is a homogeneous differential equation. The forcing function is 0, which means that I picked the right form of the solution. The form of the solution is going to be V of t is equal to some initial voltage e to the minus t over tau. So that's good news at least. Now let me rearrange this equation, multiply through by 9, so this will be 10 V of t plus 18 dV by dt is equal to 0. Now if I divide out the 18, I get dV by dt plus 10 over 18 V is equal to 0. If we have a 1 in front of this term is 1 over tau. So tau is equal to 18 over 10, or 1.8 seconds, which is the same as we got before. So if our tau is matched between two different ways of doing the problem, we're probably in really good shape. We don't have an alternate way to check the initial condition V0, so we just have to be really careful when we do that one.